Okay, so last week we did all of the gallery of graphs type questions, which were like the hyperbola, the truncus, the square root. We're going to continue on with and essentially conclude that chapter section by looking at the other kinds of questions that will come up around those particular functions, namely what are referred to as the families of functions style questions. So we've done them before in the context of like polynomials, quadratics, that sort of thing. It's basically where you have a whole bunch of unknowns in the equation and your goal is simply to solve what all those unknowns are. You'll have a bit of provided information to help you with that, and the goal is obviously to use that provided information to help you solve any of the coefficients that are involved. The way you solve families of function style questions for those graphs, the gallery of graphs type chapter, is more or less going to be the same as what we've done for polynomials, quadratics, and that sort of thing. These graphs are a bit different. They have different key features, namely the asymptote is one of the new key features that comes up with these kinds of graphs. So that's really the only difference, going to be figuring out how do we actually incorporate asymptote related information to help us solve those coefficients. So for now, what I've got here is a fully generic hyperbola. There's literally nothing that is known about it in the function itself. From there, we're told some additional information. Namely, we have a vertical asymptote, horizontal asymptote, and a point that we've passed through. Just because we have someone new attending, I'll just quickly introduce the setup. There's going to be a few separate cameras here. The one that I'm mostly going to refer to is the screen share. At the very top, you can click between the meeting window and the screen share window. The other two cameras would be my face, if you want to see that for whatever reason. And there's another camera in the meeting window itself that's aimed at a book. That's where we'll do any handwritten notes in there once we start practicing these together. But for now, on the screen share is what we're up to currently. If you have any questions about that, feel free to message me or, yeah, hop off mute, either way. But okay, so we have all this key information. What are we going to do to solve all the coefficients? Well, in the case of hyperbolas, hyperbolas are made up of a bunch of asymptotes. It has a vertical and a horizontal asymptote, and those are directly corresponding to the horizontal and vertical translations. The vertical asymptote is going to be corresponding to the horizontal translation, and the horizontal asymptote is going to correspond to the vertical translation. So this is just fundamentals of hyperbolas right now. If you shift the hyperbola right by 3, you should now get the asymptote at x equals 3. Same thing if you shift it up by 1, so setting c equal to 1, you should also get the horizontal asymptote at y equals 1. So the asymptotes will typically allow you to grab your horizontal and vertical translations. From there, there's only one unknown left, which is often the case for pretty much all of the functions that you'll ever look at. There'll be the leading coefficient a at the front, whether it's a polynomial, whether it's a quadratic, or any other type of graph. By the time you get down to one variable, you're usually solving that by subbing in a known point. So basically, you make sure that you plug in the h equals 3 to c equals 1 into the generic f of x, and then finally replace the x and y with the point that's given to you. So x equals 2, y equals -1. It's going to go there and there. There's only one unknown left, so we're just going to solve that by doing a bit of rearranging. Any questions at all as to how that has come about? Either hopping off mute or message, either way's fine. And if I go too fast, feel free to let me know. I'm happy to go back on things. But for now, let's have a look at the truncus. So very similar thing, right? The truncus has a very similar type of graph to it, the only difference being that the denominator is now squared. That's literally the only difference. Still has your vertical asymptotes, still actually has horizontal asymptotes as well. However, I've rewritten the example a little bit differently to include 2 separate points rather than both asymptotes, just to show you that you don't necessarily need specific information in a very particular order. You can actually make use of multiple pieces of information to get to the same idea. So for instance, last time we had 2 asymptotes and a point. This time we have 1 asymptote and 2 points, and you'll find that that's also sufficient for solving all the coefficients. Because at a basic level, you basically want to count the number of coefficients that you have, and you need typically at least that many pieces of key information. So we have an A, we have a H, we have a K that needs to be solved. We have information 1, information 2, information 3. It's typically how things will go. Sometimes, in rarer circumstances, some information can be denser and actually contain more than one coefficient's worth of information, but for the most part, a good rule of thumb is if you've got 3 unknowns, you need 3 separate pieces of information to get that. So how are we going to handle it? The easiest one to work with is the vertical asymptote, right? That's just directly going to be corresponding to the horizontal translation, just like it was in the hyperbola. So we're going to get h equals 1 because we want to get it to x equals 1 for the vertical asymptote, shifting right by 1. From here, because we have 2 points given, the only thing we can really do with points is sub them into our equation. So firstly, subbing in the 2, 7, x equals 2, y equals 7, and then just simplifying that a little bit. And then the other point is going to be the negative 1, 19 on 4, which we've done here. All right, we get equation 1, we get equation 2. Both equation 1 and equation 2 have the same unknowns in them, a and k. This has now become a simultaneous equation. So that'll also become relevant for different kinds of questions, depending on the information provided, more or less. So I've chosen to use elimination here to cancel out the k. You could use substitution if you really wanted to, which would just be a matter of rearranging to get one of these on its own, or even maybe one of these on its own, and then subbing back in. Elimination is just a little bit faster, but I know you can basically do it any which way you feel like. So in this case, I'm doing equation 1 minus equation 2. So you're going to do 7 minus 19 on 4. That's that. A minus A on 4. That's that. And then finally, K minus K. That was the purpose of doing the elimination, right? You do the subtraction to cancel out those Ks. Again, not the only way of doing things, but one of the more effective or fastest ways of doing it. Simplify, simplify, simplify. You'll solve the remaining unknown, upon which you're just going to substitute into either equation 1 or equation 2, because that'll leave just k left on its own, the easiest of which is probably going to be equation 1. So you can pick any of them, but this one seems a bit easier to work with. Shoving in the a equals 3 directly there, simplifying for k. It's a little bit of a different approach there. 2 points rather than a whole bunch of asymptotes. That should be more or less familiar when you're doing your linear simultaneous equations. But yeah, anything I should go into further detail on that? Cool. Last example we have here is going to be for the square root. Again, fully generic. This time I was trying to be a bit more creative with it, giving range and domain information, more specifically maximal domain information. Because technically, if it just said domain, that wouldn't necessarily directly translate to anything in the graph, because any domain could be a small part of the true maximal domain of the function. Maximal domain being all possible values that could fit in, whereas just generic domain could be any part of that. So for instance, another domain could have been like 2 to infinity or 3 to infinity. It's not maximizing it though. But yeah, we got some range and domain information, and we're told that it passes through a point. That's a very common thing to have, passing through a point, because there's only so much you can do to be creative with the other information provided. So how does it work? Well, firstly, we've got to remember the square root is the function that has like a vertex that has a starting point on it, and it just sort of ticks up and to the right as long as there's no other transformation factors involved. So probably the easiest thing to work off of would be the maximal domain of it from 1 to infinity. If the domain is maximal at 1 to infinity, it means that we need to start at x equals 1. And the only way we can do that is via a horizontal translation, which is why we're going to get our h equals 1. Apparently I actually did that in a different order. The other thing you could look at would be the range, right? Very similarly, if you wanted to start at a half, it can't go any below a half, then you have to shift it up. You have to shift the entire graph up by a half. So the vertical translation should therefore be a half as well. That's going to hit your h and k terms pretty quickly. And as we saw before, just sub in a point, solve for a, the last coefficient. Point being 2, 7 on 2. So 7 on 2 for the y, 2 for the x, and well, not much else to really talk about there. Those are all the kinds of key examples you'll come across for families of functions, at least in the context of the gallery of graphs chapter. Maybe one final thing I'll touch on is the way the actual question that's being asked could be just solve for coefficients, in which case you do exactly what I've just discussed here, right? Just give h, give k, give a, or whatever the letters are. If it says find the rule of the function, more specifically, don't just give the letters. You then also have to rewrite this entire thing at the very end with those actual numbers at the very end. And that'll be the only way you can actually answer the question properly. You won't get full marks for just giving the KHA. That's about it for the lecture portion on this. It's a fairly short little bit to add to it. Anything in there that I should clarify before we get into some actual practice? Cool. All right, let's give it a shot then. Question 1 is probably going to be a bit simple, so let's try with question 2 instead. Generic hyperbola, vertical asymptote at x equals 3, horizontal asymptote at y equals 4, and it passes through the point 0, 6. So let's give that a go. Have a read of question 2. I'll pull up some handwritten notes for us, well, some working out. And yeah, let me know when you have an idea of how we should start. Now we can crack on. I've also written down all the key information down in shorthand onto the handwritten notes bit. Vertical asymptote, horizontal asymptote, and point. Some of those can tell us some key information immediately. Any ideas what we can start to solve? Okay. I'll pull up the example as well, like a fully written. Actually, no, yeah, these are different information. Good. I didn't just copy it word for word. Nice. Okay, I've got a fully written example up on the screen share as well. We just need to convert those numbers basically into the ones that we're using here. So have a read of that again. In fact, I'll even get it as a screenshot, so maybe that'll be easier. I'll do a screenshot of that, put it in the chat, and that way you can even compare it directly to what's written in question 2. Most immediately available information there is going to be the location of the asymptotes, because they'll directly correspond to either the h or the k, depending on which asymptote we refer to. Any thoughts which is which? Okay, maybe we should do a quick revisit of what the graphs actually look like. That way we can all be sure what the information actually looks like and how the function changes things. Okay, so let's just do the basic hyperbola 1 over x. So it looks like this. We did this last week, but maybe you guys have either not done it yet or just need a bit of a refresher. So 1 over x, right, you get this sort of shape going on here. When you, so basically before anything is said and done, you have a vertical asymptote at the origin, and you also have a horizontal asymptote at the origin. So when you add a translation factor to it, shifting it right by 1, for instance, what you'll notice is the whole graph shifts right by 1, so too does the vertical asymptote. So in other words, shifting left or right, horizontally speaking, will also determine where that asymptote is going to go, specifically the vertical asymptote. So, using the information we have here, if we have a vertical asymptote of x equals 3, that means we need to shift right by 3. So in other words, that h needs to be 3. H equals 3. Very similar could be said for the horizontal asymptote. So again, if I get up my example, we can see that shifting it left or right didn't really change where the horizontal asymptote goes. This one here. What does change it is any pluses or minuses at the front here. Oh, did you have something to add? I just noticed you have mute.
Oh, okay. My audio was not working. I don't know what's going on.
Oh, well, it seems to be working fine now.
Yeah.
Were you answering things? Oh no.
Yeah.
Oh damn. Sorry, mate. Yeah, wasn't ignoring you, just wasn't coming through. But yeah, okay. So vertical translation is going to change where the horizontal asymptote is located. So +1 is now shifting it up to y equals 1. We can see it's now raised up a bit. Versus if it had a -1 there, very similar thing, but shifting down by 1 instead. So if we have a horizontal asymptote y equals 4, that's going to directly mean k equals 4 here. From there, we have a point. Who wants to take it from here? We've solved 2 coefficients. All that's left to solve is the a, and we have a point that we can use. What could we do?
You can rewrite the equation as y equals to a of x minus 3 plus 4.
Perfect. Yeah.
Then set the equation and sub in the values for the point.
That's right. Yeah. So subbing in the h equals 3, the k equals 4, and then subbing in the y equals 6, the x equals 0. 6 equals a over 0 minus 3 plus 4. 6 take 4 is 2. A over -3. -3 times 2, -6. We now have our a, we have our k, we have our h, and that's how we finish this question, because it says just find the values of a, h, and k. We don't actually go any further here by finalizing and rewriting the final equation. All that's left is probably, if you're doing it in a SAC, you'd maybe like bring these down here as well and be like, okay, cool. ... Therefore, a equals -6, h equals 3, k equals 4. That way it's all in one nice and easy spot for your assessor to look at and be like, yep, that's the final mark. Cool. All right, that's hyperbolas. That's probably the hardest one of the hyperbola section in here. So let's move on to a square root then, unless anyone wants to practice more hyperbolas. Let me know. Otherwise, we will move on to question 6. This time we have 2 known points, and we have to find 2 variables, a and h. So we know ahead of time there is no vertical translation in this square root graph, which is nice to know. What might we do?
You can
Was
form two equations with the points.
Yeah, correct. So basically we have 2 points. If we sub those into the equations, then yeah. We're doing question 6, by the way, for those who asked. Yeah, so we have those 2 points. We're subbing into the equation. So it's going to be point 1, we're going to have 2 equals a root 1 minus h. We'll stop there, I guess. Leave that as equation 1. And then the other one is going to be 4. 4 equals a root 10 minus h. And again, we'll leave that there for equation 2. Alright, we have 2 equations, 2 unknowns. That usually means 1 approach. What are we going to do from here to get our unknowns? This one is a bit trickier to work with. Square roots in there make things a bit weird for depending on how you want to go about it. Not impossible, just a bit harder than when you're doing linear versions of this, for instance. Two equations, 2 unknowns. Typically, you're doing simultaneous equations here, which means you have 2 options basically. You do your substitution approach, or you could do your elimination approach. Both will work. One, I think, is going to be easier than the other, but again, both will work, so I'm happy to take it whichever way you want to go.
We can use elimination for this, maybe.
Yeah, I think that'd be probably the fastest way to go about it. Yeah. Elimination, how are we going to implement it?
We can do. We can double the first equation.
Yep. So that'll make it into 4 equals 2a root.
Actually, wait. We can divide them to get rid of the a.
Yeah, I think that'll be a better idea, because doubling it, you see that it's going to give you the 2a, so they won't quite. Oh, they'll still cancel out, just not as easily. But anyway, so yeah, dividing it doesn't actually matter which way you divide. If you want to stick with whole numbers, then doing equation 2 divided by equation 1 will be a bit nicer, because 4 divided by 2, rather than doing 2 divided by 4. When you're actually doing your arithmetic here, it's good to literally describe what the arithmetic is that you're actually doing, because it can be a bit confusing as an assessor to know exactly what you've done here, because there are different ways of going about it. So literally saying equation 2 divided by equation 1 and giving them these labels will be helpful, not even just for your own understanding of what you're actually trying to do, but also for your assessor to understand what you're doing. Yeah, so elimination method, we're doing equation 2 divided by equation 1, so we just do each individual term divided by its corresponding spot. 4 divided by 2 gets you to 2, a divided by a gets you nothing, or technically 1, and then root 10 minus h divided by root 1 minus h. From here, we're just rearranging, right? There's only one unknown left. Yeah, in fact, I'll throw it back. Any ideas how we're going to start unwrapping this to get h back on its own? I know roots can be a bit strange, especially when they're like divided by each other.
We can both the denominator and numerator are square rooted, so we can consider it as the fraction being square rooted
Yeah,
and take
absolutely.
it to the other side. So 2 squared.
Yeah, so first step was basically consolidating the roots, and then the second step would be squaring both sides to cancel the root. Yep, so 2 squared gets you to 4. 10 minus h on 1 minus h. And then from here, this is just linear at this point, right? So they're like multiplying both sides by 1 over h, 1 minus h rather, 10 minus h. And, you know, I mean, I could continue here if we really wanted to, but actually we kind of do, don't we? Because we need both solutions. So I'll just quickly wrap this one up. 4 minus 4h equals 10 minus h. Okay, so let's get everything over. So it's going to be 3h from that, and 6 minus 6 over 3, so minus 2 for h. That's going to get us our h, but we need both h and a. What's the final thing to now get our a?
Substitution.
Yep, substitution into either equation 2 or equation 1. Both of them are very similar. Maybe equation 1's a bit easier to work with. So h being negative 2, we would now write something like 2 equals a root 1 minus 2. Just double checking. Yeah, minus 2 for h. 2 equals a root 3. 2 on root 3 equals a. Got a, got h, and that's all the question wanted, a and h. Sweet. So yeah, when you have multiple points, the approach is pretty much always going to be a simultaneous equations approach. Sweet. If there's any questions about that, let me know. Otherwise, we can move on. Actually, here's a bit of a unique one as well. Rather than give you the information in written form, it could also be in graphical form. I think we'll just more so talk about this one rather than like actually do it live workshop together. Basically, the idea is you have a generic function and you actually have the graph of that function as well. Functionally, there's no difference between getting it written versus getting it in a picture. Like for instance, if we look at like part B, we're told the horizontal, we're told the vertical asymptote, and we're told a point. That is identical to question 4. You're told the vertical asymptote, you're told the horizontal asymptote, you're told a point. So you solve it the exact same way. The root is going to be a little bit different, maybe, in the sense that the point you're given is the vertex, right? So you're given both the horizontal and the vertical component of that, and then finally another point, right? We were talking about before how it's a good rule of thumb, if you have 3 unknowns, you should have 3 equations or 3 pieces of information. This one technically only had 2 pieces of information, but sometimes some pieces of information are more dense than others. They have more in them, namely the vertex. Kind of like how it worked for quadratics when you had the turning point. You had both the horizontal and the vertical component in that. Same thing here. H is going to be 1, K is going to be negative 2. Yeah, that's about it really. You'll see there's also circles and maybe, yeah, I think we saw the y squared equals x as well. Those are other graphs that are covered in these chapters. You might also notice they have asterisks with them. That's because they're not explicitly in the study design for methods, either in Unit 1 and 2 or in 3 and 4. They are there because they are relevant. We did briefly cover what the graph of like y squared equals x would kind of look like, but only because it helped us a little bit with understanding why the root looks the way it does and why we get sometimes some strange and interesting behavior with it. But basically anything with in fact we didn't touch circles at all. So anything circle related or anything y squared equals x related has never made an appearance in an exam and is not explicitly in the study design. So don't feel like you have to be doing those as well in your private study. Cool. I mean, that'll be about it for those. Unless anyone wants to practice more of those kinds of questions, I did also have the chapter review section in here for the agenda today, just so we can practice all sorts of stuff regarding these graphs rather than just the families of function stuff. So I'll scroll down to it, but if someone wants to practice more of those kinds of things, let me know. I'm more than happy to go back to it. If not, we'll start from question 2 here, because I'm noticing question 1 is the y squared equals x graph. So, question 2, we have a linear, oh, it's still y squared equals x. Never mind. Okay, let's do, is this going to be this should be fine. It looks a bit weird, but I think it's going to be fine. Question 3. We have a generic square root graph with just a horizontal and a vertical translation. No dilation factors involved. We're trying to prove that if this curve, the square root curve, meets the line y equals x, so it touches it at some point, then A must be a solution to this. So in other words, whatever this comes out to be as having met that point, this needs to resolve as 0 on both sides. That's a tough question to start with. Jeez. Okay. I'm not immediately sure what to do here specifically. We do know one key piece of information, which is that this meets that. So there's usually one thing we do there when we know that equations touch each other. What's typically the case that we should follow up on if equations are touching or meeting at a certain point? Ignoring the complexity of it, even if it's just linear touches linear, what do you usually do in your working out steps when graphs meet each other? Have a think about that while I define some functions in the cars. Okay, so usually a good point of reference when we know that functions touch each other is to equate them to each other, right? If they both cross over at a certain point or touch at a certain point, it means that we can figure out roughly what that point is going to be, or at least take steps towards finding out what that point is going to be by equating the two equations together. Equation 1 is the square root, equation 2 is the graph of y equals x. So a decent starting point would be to make those two equations equal each other and see what we get. A nice and nasty plus minus square root, which makes sense. We were kind of talking a bit about how the square root can give a bit of weird results. namely because when we're dealing with the square root, we only take the positive or the negative, depending on the sign at the front of the square root. When you're actually doing your algebra, that's not necessarily reflected in that. So only one of these roots is going to be valid. Either that'll be the negative root. Yeah, that'll be the negative root, and this one here will be the positive root. Which one of those, I know they're complicated, but just think about this one as the positive, this one as the negative. Which one should be valid for a graph like this? Or at least most likely to be valid. Okay. So the basic square root graph without any transformations on it goes like that. As for the graph of y equals x, something like that, right? So we know from the equation in question 3 that there's only vertical and horizontal translations to it. So this green line can only be shifted up, down, left, right. It'll never go back on itself, it'll never go down through here. So there's only really a couple of ways this can work. More often than not, it's going to be intersecting on this positive side here, namely because of the direction it's headed in. So it's a good, decent idea to probably just start with the positive part of that root. Not to say the negative is impossible. Right? You could have the square root starting over here and therefore cut twice. But just based on the overall direction of it, and because we can't really work too well with plus minuses, we've got to at least pick one of them. Let's work with that. But just for simplicity's sake, I'm going to take this one. Now, we're told the curve meets y equals x at the point AA. When you equate two equations together and solve for x, you're getting the x-coordinate of that spot. So in other words, if we're told that it meets at AA, and the x-coordinate is equal to this, or at least could be this, could be the plus or the minus, then that is going to be our A value. More specifically, I don't really know if the wording is meant to imply this, but meeting a line isn't necessarily it's not like explicitly defined. I think the idea is that it's supposed to only touch at that spot, not cross over multiple times. I'm just going to quickly double check that because it's not explicit. It's not strict wording there, and it will matter how you handle it, whether or not you have to care about both the positive and the negative. Let me just double check that. This was question 3A. Yeah, okay. Doesn't really give a whole lot of guidance there. Because the idea there was if it only meets once, then the square root term should condense down to 0. Because the only time you have two solutions is when the square root is non-zero. So I was thinking maybe we could possibly just get rid of that. And that'll get a relationship of A being 2c plus 1 over 2. So that simplifies things quite nicely. From there, satisfies the equation a squared, all of that. There's still 3 unknowns there though, because we could rearrange and at least cancel one of those out. We're still going to have 2 unknowns. What are they actually doing here? If you sub in, you'll have 2 left. I mean, I guess the other thing we could do would be, if the point A exists on both, then you could sub that into either equation 1 or equation 2. The square root graph is going to be a lot easier to do, well, a lot more informative. Otherwise, you just have A equals A on one of them, which I believe was the approach the solutions took. So let's see where that gets us. So if we sub in AA as both the x and the y, we're going to have A equals square root A minus B plus C. Then from there, what I believe they did was get everything on one side and leave 0 on the other. And because there's a bunch of squares involved, that would be a matter of getting all this over. Let's have a look. So you'd have A minus C, by getting the C over, squaring both sides, A minus B, bringing back these over, A minus C all squared, minus A plus B equals 0. Yeah, okay, it's getting closer. Expanding this one out, A squared plus C squared minus 2AC, because it's AC, and it's negative, minus A plus B. Yeah, okay, that's what they meant. Very strange question. You don't usually do stuff like this, but I guess that's what we're doing here. Nice lesson for even myself to learn. Then from here, just collecting like terms. So they wanted to have A squared at the front, so let's put our A squared at the front. Then they wanted to have the A term, so it's going to be minus 2AC and minus A for a total of minus bracket 2C plus 1. So you take the 2C out of that and the remaining coefficient of 1 off of that. I've also taken the negative out, just like they had in the question. And then finally, the C squared, we left that over, so bring the C squared over, and the B just stays exactly where it was. Alright, that was a different approach there. So I guess the lesson there is, these kinds of things, sometimes you have to do multiple takes at it. Right? Like typically when you have equations that meet or intersect, one of the things you would typically do is equate them to each other. But in this case here, it was more prudent to do the other approach, which is if you have a point, try subbing the point. Bit of a strange one, but we got there. I know we took a detour around it. Does it make sense now how we got there? It was just a matter of subbing in the point into equation 1 and then rearranging until it looked like what we had in question 3a. Sweet. Alright, BI. If the line with equation y equals x is tangent, show that c equals 4b minus 1 over 4. That sounds a lot more like what I was doing before with equating them together and the whole discussion about the roots cancelling out, because when it's tangent, you're only just touching along the side of the line. So for instance, you have the square root graph. Well, I guess we'll do the line y equals x first. And then when you draw your square root, it should only touch off of that. So have one intersection point. the only time you ever have more than one intersection point is when you have plus minus on your root. But if your root term is 0, then you should only ever have one solution there. So that should mean doing this sort of thing should help us a bit. We got our two solutions. We know, I guess we don't want to sub in A into this time because in part BI there is no A involved in there. Oh, actually, it could also just be using the equation we just created in part A. If y equals x is tangent, then we could do like a discriminant thing on that and only get one solution off there. But maybe we'll play with this a little bit more. So we would have x equals, but there's also no x there. Yeah, okay, that's probably why it doesn't really work out too well, because you've still got one additional unknown that's left here. A being equal to 2c plus 1 over 2. Yeah, it looks close, but it's probably going to be a dead end there. Because even rearranging this for c, you're going to have 2a minus 1 all over 2. So it's out by a factor 2. So probably using this equation here would be appropriate. Because what this equation is simply what you get when subbing in that point, AA. Now, the solutions to this, what do we do here? Do you discriminant this and let discriminant equal 0 for one solution? That's usually the case, because that'll get you only C's and B's involved. Yeah, I think that should get us there. That's usually the way you go about doing the one solution type things, or tangent things. You do discriminant equals 0, because that'll get you one solution of your quadratic. So, that being the case, it's hard for me to have both of these things on the same screen, so let me just try this instead. So, for discriminant, you need b squared minus 4ac. This is your b term, this is your c term, and this out here is your a term. So let's try that. So solve b squared, so that'll be double bracket negative 2c plus 1, so b squared minus 4 times a, which is 1, times c, which is, in our question, c squared plus b. B squared minus 4ac equals 0. And this one is solving for c. Yeah, okay, that's what they wanted. That's there to validate whether the approach is going to be effective or not. This being a show that, you then have to actually do that. Do the actual arithmetic on that. I'll take a stab at it. Yeah, why not? So, let's actually prove it. So, essentially we're trying to do b squared minus 4ac equals 0, not with these ABCs, that's just the generic quadratics ABCs. So in other words, this thing here is the A, this thing here is the B, and this group here is the C. Negative bracket 2c plus 1 all squared minus 4, A which is 1, C which is c squared plus B, and that is equal to 0. Discriminant equals 0. So we'll do this just because the complexity of the equation, you probably want to see how you could potentially do this in a way that you don't make too many errors. I might make an error, I guess we'll see, but the idea, hopefully, is that this will help you with your working out. So first things first, I'd probably expand this out twice, so the squaring means the negative is going to end up cancelling on it, leaving you with just 2c plus 1, 2c plus 1. The 4 and the 1 are going to combine into each other, 4c squared, 4b. But there's a negative on that, so it's negative 4c and negative 4b. Zero. 2c and 2c, 4c squared, 1 and 1, 1, and then 2c, 2c, 2c and 1, 2c and 1 for 4c in total. Minus 4c squared, minus 4b. Collecting some like terms. Oh, nice. Those are going to cancel. 1 plus 4c minus 4b equals 0. And here is where things get a lot easier. We've done all the complexity. The question has asked us to solve for c, so we're going to get the c on its own. 4c equals 4b minus 1, c equals 4b minus 1 on 4. Cool. That was a nightmare, but we got there. Yeah, this is definitely a step up in complexity from the questions we were doing, so maybe this might be better if I just sort of demo them, unless you guys have ideas on how you want to approach them. So is it fair enough there, the whole idea of why discriminant being 0 actually gets us there? It's not something I've talked about too much. We'll definitely talk more about it in calculus when you start doing tangent lines. Is there anything I should clarify further about that approach, why that worked? Cool. That'll help us out with double I. So now instead of having a generic square root, we have a known square root of x minus a quarter. And we want to figure out the coordinates on the point of the graph for which we have, for which we're tangential to y equals x. So that same picture I had before, it just brushes up against the side. Everything we've done in I, and even in A as well, helps us with that. So we could go all the way back to fundamentals and do exactly the same thing as before, but now with the numbers instead. So we would sub in the generic point, find discriminant of that thing, and then instead we'll have numbers instead of letters. Alternatively, we also just have some helpful solutions here for us. So we know, based off of BI, that as long as C is equal to 4b minus 1 all over 4, whatever, as long as the C and B are related in that way, whatever you choose for them, you will be tangent to y equals x, which is our goal here. We're trying to be tangent to y equals x. We just want to find the coordinates of this specific thing. So one thing you can do to save time, because you've already done a lot to get to this point, is make use of that relationship. The C and the B that existed in part BI came from the question 3 square root, where B was the horizontal translation and C was the vertical translation. If we compare that to the equation in double I, square root x minus a quarter, basically you have B equals 0 because there's no horizontal translation, and you have C equals minus a quarter because that's our vertical translation. So with that in mind, we should then be able to use those two values in our equation to help us with getting that coordinate. Because remember, the coordinate is going to be AA, whatever that is. We have a C value, we have a B value, and the only other equation that we have with A in it came from part 3A. Because remember, that's just a generic thing that exists for all square roots that have horizontal and vertical components, even if those components are 0. So we should be able to plug those in there and solve for a. Let's see if we can get it. So we have a squared minus 2c, where c is minus a quarter, plus 1 bracket a plus c squared. Oh, actually, why am I doing this by hand? This isn't a show that we can just cas this out. I'll just write down exactly what we had before. Bracket 2 bracket minus a quarter plus 1 times a. Then we had a c squared, but again our c is negative a quarter. So plus minus a quarter squared plus b, where b is 0. This thing only has a in it. We get a as a quarter, which means the point AA is going to be a quarter. Just to make sure, let's see if that actually is the case. So if we sketch the graph of square root x minus a quarter, we get that. Sketch the graph of y equals x, we get that. And maybe we'll zoom in a bit more. So we'll go from 0 to 1 on that. And we'll get our analyze graph tool to find the intersection. And there it is, quarter. Obviously it's going to give it in terms of decimals because of the nature of the graphing tool. But otherwise, yeah, this is the sort of thing you do to make sure you're getting the right answer. As for proving that it's not just a solution but tangential, if your fundamentals are good enough, knowing that this whole equation and everything involved in it was discriminant based and was getting you, was all based on getting one solution, then you should be fine to not necessarily have to prove that to yourself. But even just by going off of the look at the graph and using the graphing tools, you're not going to find any more solutions off of this, right? We can prove, or we show that the only solution here is a quarter. So these are definitely on the harder side for sure. I didn't expect these to be quite so hard, but that's extended response for you. So up until now, we're looking more so about the graphing of things, how you can find the unknowns in an equation. This is taking that up to like 11, because this is still technically just families of functions questions, right? You have B and C, that's unknown. Question A was worded a bit weirdly. Everything else was a bit more like what you would see in an actual exam. So if anything, it'll be a nice little benchmark for you to be like, okay, this is what's actually required as far as when you get to your final exam, or at least similar, except for 3A. 3A was strange. Is there anything about that I need to clarify further? We've only got about a minute left, so I'll be happy to stick around for a bit longer if anything about this needs further clarification. Otherwise, yeah, I guess I can give you back the remaining 30 seconds or so that you have.
Have a good day.
You too, mate. Take care.
Thank you.
No worries. Thank you. Got a question for me? We zoned out entirely. Went too complex.